So the group are dealing with basically two main topics, nonlinear fluid dynamics and nanoscale or microscale flows and rheology. You have the interface between physics and biology very often, and I think you'll make for a very great talk. So thank you very much. The floor is yours.
All right, thank you very much for the introduction. Thank you for the invitation to spend the week here. I'm really looking forward to it. I'm sure that I'll learn a lot. So my talk today. Oh yeah, that's okay. There we go. Okay, so my talk today is going to be one of a couple talks on fluid dynamics of polymeric liquids, which is a little bit out of the main theme of the workshop. But I'll talk about some potential connections between this topic and some of the things that the more people might be interested in terms of analogies between polymeric flows and plasmas. That's working now, right? Nothing's working now. There we go. Okay. First of all, I just want to acknowledge the person who did most of the work that I'll talk about today. Great postdoc, Manish Kumar, and this has been work that's been supported largely as part of a DoD, Department of Defense grant that I've had over the last few years. So the basic observation that forms the heart of this talk is something that's been known for a long time, and that's if you add a small amount of very long chain polymer molecules to a fluid, then you can dramatically reduce energy losses in the turbulent flow regime in situations where in laminar flow, essentially nothing will change. In fact, adding the polymer increases the shear viscosity of the fluid, increases the drag in the laminar flow regime, that leads to very large decreases in drag in the turbulent flow regime. This is a phenomenon that's been known since the 40s. It's widely used in a lot of industrial processes, including transport of crude oil. You can get similar effects from solutions of surfactants that form what are called worm-like micelles. So they form micelles that are sort of polymer-like, and those are very effective in aqueous systems for drag reduction. There's an interesting experiment just a couple of years ago. A civil engineering group added polyacrylamide, which is a very inexpensive long chain polymer. They added it in large quantities to an irrigation canal, and because of the drag reduction, because the friction is lower, for the same flow rate at steady state, you would have a lower elevation in the canal. And the motivation for this study was flood remediation, that you could potentially lessen the effect of floods by adding polymer solutions, lower the drag and lower the elevation. That turns out, unfortunately, to be very timely given flooding in Texas, the U.S. this past weekend. This is the phenomenon that I'm interested in. So we want to gain some fundamental understanding of what's going on in the flow and the interaction between the turbulence and the polymer dynamics that leads to this drag reduction phenomenon. This is a picture. This is probably 50 or more years old. It's from the New York Fire Department. They did an experiment. So this is Union Carbide, which no longer exists. They marketed something called Rapid Water, which was basically a polymer solution. And this is a demonstration in the New York Fire Department of pumping water here, you can see the stream of water. You can see these are firefighters over here. And the stream of this water plus polyethylene oxide, or rapid water, and presumably this is the same pressure drop, and so you're getting substantially larger flows here. Okay, and so there was this idea that you could use this in firefighting. All right. So why isn't it used in firefighting? So I got in touch with someone who sells equipment to firefighters and asked this question. And here's what he led me to. So in FDNY, New York Fire Department, rapid water was used only for a few years. If you bled the line in the hallway and the proportion was incorrect, the floor became very slippery. So this was actually hazardous to the firefighters. And so, so they didn't use it for firefighting. Though I never heard of this myself, but apparently there was some idea that you could use it for crowd control and make everybody slip and fall. I haven't actually heard that that's been done. But anyway, that's why it's not used in firefighting. Okay, so with that as kind of a general background, let me just say a few words about dilute polymer solutions, just as background and nomenclature for my talk. So a long chain polymer, flexible polymer at equilibrium has a conformation that essentially looks like a random walk. Okay, if the molecule is flexible enough, if you go a little bit along its backbone, the backbone has reoriented, and so it looks like a random walk in space. Okay, so that's it at equilibrium. And so there's a mean squared or an end-to-end distance or radius of gyration that has random walk thickness, right? So the radius goes as the square root of the number of segments in the chain. Now, in terms of modeling, we are not going to try to model all of the degrees of freedom of this polymer molecule. You can do analysis of this, and the degrees of freedom that correspond to shorter and shorter segments of the chain have faster and faster relaxation times. And in many cases, it's adequate, at least qualitatively, to just model this long chain polymer as a bead spring dumbbell. And the spring here is essentially representing the entropic restoring force. The Brownian motion wants to drive this thing back toward a random coil. And you put two beads here. Each of these beads experiences a Stokes drag. And so essentially this end-to-end vector Q, it wants to stretch like a material line, but with a relaxation back to equilibrium. And I'm going to say a little bit more about this on the next slide. Okay. So this molecule, it has a diffusivity. It has a relaxation time lambda, which is going to be really important. The relaxation time is related to how long it takes the polymer to diffuse its own length. So that's a scaling argument for the pet parameter dependence of the relaxation time. And then in flow, the important quantity that has to do with the polymer is what's called the Weisenberg number. And that's the product of the relaxation time, typically the longest relaxation time in the polymer solution, times some sort of deformation rate. And so I'll talk about Weisenberg number a fair amount. All right. There's another quantity. It's actually it's not a property of the flow. It's called the elasticity number, which is the ratio between Weisenberg number and Reynolds number. And we'll be interested in relatively small elasticity. Right. So we can think a little bit about kinematics. So we know that Q wants to stretch like a material line. In a simple shear flow, material line stretching is linear in time. And the polymer molecules, they won't become strongly stretched in a simple shear flow. And so they'll actually, because of Brownian motion, they'll stretch and tumble in a shear flow. And so the shear viscosity doesn't increase substantially. And this quantity beta here, this is the ratio of the solvent viscosity to the total viscosity. 1 minus beta is proportional to the polymer concentration. And for a dilute polymer solution, 1 minus beta is close to 0, or beta is close to 1. Right? That's what characterizes a dilute solution. Now, in an extensional flow, things are very different. In an extensional flow, the polymer molecules, the material lines, will tend to stretch exponentially fast. And so that means polymer molecules, which want to stretch like material lines, they will also tend to stretch exponentially fast, and at the same time trying to relax back to equilibrium. And so in extensional flows, if the Weisenberg number is sufficiently large, the polymer molecules will become very strongly stretched in that flow. Okay, and even if beta is close to, if 1 minus beta is close to 0, the extensional viscosity, it's proportional to 1 minus beta concentration, but it's proportional as well to the degree of stretching. All right, and that degree of stretching can be very large. So even in a dilute solution, you can have very large contributions to the extensional viscosity in a polymer solution. And that's important because chaotic flows, turbulent flows, kinematically, those are extensional flows. From the Lagrangian point of view, a turbulent flow is an extensional flow. There's a material line stretching rate. Okay, and so polymer molecules, even at low concentrations, can have large effects on a turbulent flow because of the stretching nature. All right. So I made this slide for this group because I think there are probably a lot more people here that are familiar with plasma physics, plasma fluid dynamics, magnetohydrodynamics, than with polymer fluid dynamics. I'm not at all an expert in magnetohydrodynamics, but there's an analogy between magnetohydrodynamics and viscoelastic fluid dynamics that's been pointed out that I think is quite interesting, and so I wanted to say a few words about it. So again, I talked about material line stretching. So if you have some material line, I'll call it delta x, this is the evolution equation for delta x. And so if this thing, if the transpose of the velocity gradient, if that thing has a positive eigenvalue, then you'll have exponential stretching of material lines. Okay. The polymer molecule, same picture as the previous slide, that polymer, the end-to-end vector of that polymer molecule, modeled here as this dumbbell, also wants to stretch like a material line because each of the beads wants to move. If you cut the spring here, each of these beads would just move like a Brownian particle. Right? So they'd follow the material lines with some Brownian motion. So we have the material line stretching here, the relaxation due to the spring, and then C is just as a random force, or a random displacement. And then the stress tensor associated with the polymer molecules is related to the dyad, the outer product of Q with itself. The angle brackets here are just an ensemble average. Okay. And so the evolution equation for this dyad here, right, these two terms come from the material line stretching here. This term here is a relaxation term that comes from the spring. Okay. In the magnetic field in an electrically conducting fluid, the magnetic field vector B, this is the evolution of B along a particle path. So there's also a material line stretching piece, and instead of relaxation, there's a diffusion. The Maxwell stress tensor, again, is proportional to the dyad of the magnetic field with itself. And so if you think about that, the evolution of that dyad, it has a term that's exactly the same as in the polymer case, but it has a relaxation term that's different, diffusive term rather than a relaxation to equilibrium term. So this is an analogy that was pointed out in a JFM paper from Ogilvy and Proctor a little more than 20 years ago. Like I said, I'm not a plasma physicist, don't know anything about magnetohydrodynamics, but there's an interesting analogy. And people have pursued this in a number of contexts. People have done experiments in Taylor-Couette cells, Taylor-Couette flows, to draw analogies between instabilities in curved streamline polymer solution flows and in some astrophysical flows. There are some experimental observations in polymer solutions that have been interpreted as being the elastic analog of Alfvén waves. All right, so there's some connections between polymer and magnetohydrodynamics. All right. Okay, so back to drag reduction. Just in terms of some further features of drag reduction. So this is just friction factor versus Reynolds number for pipe flow. This would be the laminar flow case. This is the Newtonian turbulent case. And one of the things that's really interesting about polymer solutions is that there's this so-called maximum drag reduction phenomenon that this is just data from a large number of different systems. And there's essentially a new universal curve that all of this data collapses onto. And it's between the Newtonian turbulent curve and the laminar curve. And down here near transition, this curve runs right into the Newtonian laminar case. And so this actually is the regime that I'm going to be really interested in down here. Okay. And it's been known for a long time that the turbulent structures in this regime, they're substantially weakened. The quasi-streamwise motions of wall turbulence get suppressed, and I'll talk about that in a moment. The Reynolds shear stress nearly vanishes, which means that the polymers are carrying the stress fluctuation, not the turbulent flow. Okay, and then this is from some DNS results from Anthony Barris's group. Didn't come out all that well. So this is just looking at streamwise velocity near the wall, and in the Newtonian case, you can see the quasi-streamwise vortex structure. So here you're looking at the streamwise velocity. You have the near wall quasi-streamwise vortices that are bringing slow-moving fluid up from the wall. So you have negative fluctuations in streamwise velocity there. And then you're bringing fast-moving fluid down from the bulk, and you have high-speed streaks or high positive fluctuations in the streamwise velocity. So this is completely characteristic of Newtonian wall turbulence. And this is in the case of drag reduction. Here, the Weissenberg number is 50. You see, this is all of these fluctuations are tending to be smoothed out. All right, and the length scales of these streamwise vortices becomes much larger. All right, and there are experiments essentially indicating that at a high Weissenberg number, these streamwise vortices nearly vanish. All right, so this is one of the somewhat mysterious aspects of the drag reduction phenomenon, is that the streamwise vortices are what sustain Newtonian turbulence. Okay, there's a self-sustaining process for those streamwise vortices. They're nearly vanishing in the case of maximum drag reduction. And so then there's a question of, well, what's keeping the turbulence going? Why doesn't the flow just become laminar? All right, and that's what I'm going to spend some time talking. Okay, and so our first studies of this, which were quite a while back now, we got interested in the question of what is the polymer doing to the near wall turbulent structure, the quasi-streamwise vortices near the wall. And the way we examined this was by looking at so-called exact coherent states. So an exact coherent state, there are several families of these. They were originally discovered by Fabien Willeff and Willeff and Nagata back around in the early 1990s. And what was found was that the Navier-Stokes equations support nonlinear traveling wave solutions that have 3D quasi-streamwise vortex structure, which is the basic structure of near wall turbulence. These are in cases where the laminar flow is linearly stable. And so these 3D nonlinear traveling wave states, they arise in saddle node bifurcations at finite Reynolds number. And they're very nice as models of near wall turbulence because as traveling waves, they have relatively simple structure. And in the right reference frame, they're steady states. And there are other families of these exact coherent states that are modulated traveling waves, relative periodic orbits. If people have questions, I can talk more about that maybe this afternoon in the Q&A or even this morning as well. But what we decided to do was use one of these traveling wave exact coherent states as a model to try to understand what the polymer was doing to the near wall turbulence. All right, and so we did this in the channel flow geometry. And so what you're seeing here is the bottom half of a channel. This is a quite low Reynolds number. So these are transitional Reynolds numbers. Newtonian transition in channel flows at about Reynolds number of 1,000. And so the panels here are the degree of streamwise polymer stretching. And you see the vortex cores here that we've plotted with the Q criterion in the flow gradient direction. And so this is relatively low Weisenberg number. Here are staggered quasi-streamwise vortices here. And you see the fluid is being carried up from the wall, near the wall. So the strain rate is highest, the shear rate's highest at the wall. So you're carrying stretched polymers up into the fluid. Here, we've increased the Weisenberg number and the Reynolds number. These experiments, these simulations, we did a constant elasticity number, or ratio between Reynolds and Weisenberg number. Here are the vortex cores. Now you're starting to see larger polymer stretching. And here, Weisenberg number 41, what you see is now the regions of the quasi-streamwise vortices, they've become much weaker, okay? And what you're seeing now is the stretched polymer that's being carried up from near the wall. Now that stretched polymer is wrapping around these quasi-streamwise vortices. Yeah, Drew.
Quick question. So the Weisenberg number is a ratio of some flow scale to the polymer scale. Which flow scale are you using here?
So here we just use the wall shear rate, the nominal wall shear rate. Yeah, that's right. The number would change depending on the specific value, the specific choice that you made. But I think here we just use the laminar centerline velocity divided by the channel height, which is proportional to the wall shear rate. Yeah. And yeah.
Probably depends on concentration, but do you need to consider flow or it can be...
Yeah, so here Mach numbers are very low. We're considering these to be incompressible flow. Yeah, even with the polymer. That's right. Yeah, so that's, I mean, the polymers are present in very small quantities. Even polymer melts where there's no solvent at all. Those are incompressibility is a very good approximation for molten polymers. So yeah, in this case, we can assume incompressibility. Yep. Okay, so anyway, coming back to this picture here, you see the polymer stretching, wrapping around these streamwise vortices. And if you think about the divergence of the polymer stress, so the force that's being exerted on the fluid, what's going on here is actually that the polymers are wrapping around, and now the flow in the vortex cores is a rotational flow. It's not stretching the polymers. It's becoming close to rigid rotation. So the polymers relax as they get rolled into these vortices. And so what's happening here, you think about the divergence of the polymer stress is leading to a net force back this way. And so that's tending to unroll these streamwise vortices. It's working directly against these streamwise vortices and tending to suppress them. And so you can see this very, very clearly in these nice exact coherent states because they're just in the right reference frame, they're just steady states. But people have also done full direct numerical simulations and found very similar observations. Okay, so mechanistically, we understand how the polymer molecules are suppressing the normal streamwise vortices of the near wall turbulence. Okay? And so, we can, with these exact coherent states, we can look at the bifurcation diagram. We can look at where these coherent states are existing. And so that's what we've done here. This is just a parameter space of Reynolds number versus Weisenberg number. Above this case, this is where those exact coherent states or these quasi-streamwise vortices exist. And a path, an experimental path, is sort of an oblique line through here. And so you come into this case where these coherent states exist, right? You can actually leave that region as well. Here's a schematic. You can have one experiment that enters this region where these coherent states exist. And then as those quasi-streamwise vortices get suppressed, it can leave that region. You can do another experiment at higher elasticity number where you never enter this region. But experimentally, you won't continue to be laminar. You will eventually move to a level of large drag reduction. And so this was at the time, this was just a conjecture. It's 2006, right? That there's some other transition phenomenon here that's keeping you from staying laminar. And so at the time, we felt like, okay, we understand how these quasi-streamwise vortices get suppressed, but then it's unclear what happens after that because the flow doesn't laminarize. Polymer drag reduction doesn't correspond, except in very limited parameter regimes, to the flow laminar. So we made some conjectures about what might be happening in that regime, other types of coherent traveling wave states, maybe with different length scales. We conjecture that maybe Tolmin-Schlichting waves might become important, though they're not conventionally important in transition to turbulence because they don't, first of all, in pipe flow, they never go in, there's never a linear instability. Even in channel flow, transition to turbulence happens well before there's the linear instability, and the turbulence looks nothing like the linear instability. All right, so we were kind of left with this mystery of what's going on after the quasi-streamwise vortices get suppressed. Right, so that's the rest of the talk. In about 2013, there were some very interesting observations from Björn Hoff's group and particularly Yves Dubiel. So they observed a phenomenon that they called elasto-inertial turbulence. From the experimental point of view, they did some very careful studies that showed now an instability, seemingly a linear instability, and I'll come back to that, of the laminar flow that was leading directly to this maximum drag reduction asymptote. So actually experimentally, people, Jack Zakin and others, had observed something very similar many, many years ago. But what was particularly significant was that Yves Dubiel did very careful simulations and found a region, a parameter regime, where the quasi-streamwise vortices were essentially absent, and the flow was replaced by something with vortices that were whose cores were perpendicular to the flow direction, and with a polymer stretching structure that had a very, very strong sheet-like nature, which you see here. Okay, and so these were the first computations to kind of suggest what flow structures might be occurring in this, and in particular, what stress structures might be occurring, because you can't measure the stresses. So these are the first hints of what might be happening after the quasi-streamwise vortex states have been suppressed. All right, and so we got very interested in this phenomenon. One thing that's important is that now, in contrast to Newtonian turbulence, which is inherently 3D, if you do a 2D simulation, 2D Newtonian simulation, you don't get turbulence. You can't get quasi-streamwise vortices, and those are the structures of the near wall region. In these regimes of so-called elasto-inertial turbulence, that's self-sustaining in 2 dimensions. And so what we focused on then was two-dimensional simulations. Okay, so one thing, some later experiments found that there's a path to elasto-inertial turbulence that involves relaminarization, and that actually is predicted as this diagram that we speculated back in 2006. So here they did these they did quasi-static experiments, slowly increasing the polymer concentration. All right, and this is at Reynolds number 3150 to start Newtonian turbulence. They eventually found in this intermediate concentration regime that you relaminarize, and then at higher concentration you go back to some new fluctuating state, non-laminar state. You go up to Reynolds number 5200, you don't see this relaminarization. Okay, so you just kind of have this smooth transition between the Newtonian friction factor and the elasto-inertial turbulence friction factor. All right, what this really clearly pointed out, which is what people had inferred previously, is that there are two types of turbulence in polymer solutions. There's low Weisenberg numbers. There's basically elasticity modified Newtonian turbulence with quasi-streamwise vortices, and then at higher and that version of turbulence, the Newtonian version of turbulence, is suppressed. But then there's an elastic version of turbulence, or elasto-inertial version of turbulence, that's promoted. All right, and that becomes very clear here in this picture. Okay, and so those are the phenomena now coming to what we've been doing most recently. Those are the phenomena we want to understand. Okay. So we'll talk about this reentrant transition. I'll talk about some linearized analyses, and then connections with modes that show up in the linear case. And what's really kind of laid things out for us very clearly is we started doing viscoelastic version of spectral proper orthogonal decomposition. That's what I'll close with, and you very clearly see how the structure decomposes in that case. Okay, so just to be specific, so I talked about this bead spring model of a polymer molecule in solution. We're going to use a bead spring model. In our case, we're going to use the so-called Feeney-P model, which is where the spring has finite extensibility, which is just a reflection of the fact that the polymer molecule can't stretch forever. It's got a contour length, and it can't stretch beyond that. Another aspect of the model. So in reality, so this is the evolution equation for this conformation tensor QQ. In reality, there's a very, very tiny diffusion term, because the polymer molecules, they have a finite but very tiny diffusivity. Classically, that diffusivity is neglected, but that causes numerical problems. And so we add a very small but still artificially large stress diffusion. Okay. We're going to work in the Reynolds number regime, which is really the transitional regime here. Okay, so weakly turbulent regime. All right. Beta in all of our simulations will be 0.97. So these are dilute solutions. Okay. All right, and then we're just working channel or pipe with periodic boundary conditions. All right. Okay, and we use a really beautiful open source code called Daedalus. It's a spectral code. It was developed by some astrophysicists. It's a very flexible PDE solver using spectral methods, and so I recommend looking into it. Okay, and so the first result, actually, this is the pre-Daedalus. This is an old code. We wanted to see if we could find this reentrant transition that Björn Hoff's group had found experimentally. And so we did this, keeping the concentration the same, but increasing the Weisenberg number. This is just friction factor again. Here's the Newtonian case. We increase the Weisenberg number. This is at Reynolds number 1500. We increase the Weisenberg number. the friction factor goes down, so you have turbulent drag reduction, and then we see a drop to laminar. So the flow becomes laminar, and then as the Weisenberg number increases, we see a transition back to a completely different state. Actually, I'll point out that this requires finite amplitude perturbations. The flow remains linearly stable in this regime. All right, this is the vortex structure in this regime. So this is Weisenberg number of 7, and so you see quasi-streamwise vortices. The color coding is just distance from the wall. Up here, this is Weisenberg number of 20. That's just in this EIT regime. Now you see vortex structures in the neutral direction. Right. So here's this reentrant transition, the laminarization from this going back to elasto-inertial turbulence here. Okay, so we see the same thing that's found in those experiments. All right, it's a different path through parameter space, but it's still this reentrant transition. We start looking at the structures of that, and one thing that popped out very clearly right away is if you look, this is the polymer stretching. That's the colors here. What you see is the polymer stretching fluctuations are very localized in regions near the top and bottom walls. And so that's the first hint of connections to linear instabilities in this parameter regime, which I'll talk about in a second. And there's this important concept of critical layers, which is a region, which is a surface in a flow where the wave speed of a perturbation equals the local mean velocity of the fluid. And so that's the position in space where energy can be exchanged between the mean flow and the fluctuations. Okay, and we're seeing hints of that in the localized stress fluctuations. This same type of structure has been observed in other simulations. This is from a pipe flow simulation, again from Björn Hoff's group. It's not super clear there, but these are actually Q fluctuations localized near the wall. These are Q fluctuations. This is again from Dubiev and collaborators, where you're seeing these localized fluctuations. Okay, so this sharp localization of fluctuations. This is a hallmark of elasto-inertial turbulence, at least in the parameter regime that we consider. And so where does this come from? So many of you probably are familiar with linear stability, classical linear stability. So in Newtonian channel flow, there's a linear instability, Reynolds number 5772, where the so-called Tolming-Schlichting wave goes linearly unstable. The critical layer there, again, the wave speed of the perturbation is equal to the mean velocity. What's interesting about the critical layer is the kinematics here. So there's this familiar Kelvin-Cat's eye structure. And one thing that's important kinematically about the Kelvin-Cat's eye from the point of view of polymers is the Kelvin-Cat's eye structure has hyperbolic stagnation points in the reference frame moving with the mean velocity. Hyperbolic stagnation points, those are regions of large local extension. Those are regions where polymers stretch. All right, and so there's a natural mechanism for polymer stretching in this critical layer, in the Kelvin-Cat's eye kinematics. We know that the Tolming-Schlichting waves are the bifurcation is subcritical. That you can have linearly stable laminar flow up to 5772, and then transition actually in the Newtonian case happens down at 1000. So TS waves, they don't matter for Newtonian transition. Okay. And so we back those original DNS results. This is the picture that I showed before. We can just do some filtering, and you see now a very clean structure. And then these are the wall normal velocities. This is what the Tolmien-Schlichting mode looks like for the viscoelastic case of that Reynolds number. And you see this very strong similarity between the two. And here we've actually highlighted where the stagnation is. And then we've also done resolvent analysis, which is basically looking at the modes that have the maximum amplification in the linearized case in an input-output sense, and these have the same kind of structure. And so from these results here, we clearly see that something like the Tolmien-Schlichting mode is very important in this parameter. Okay. All right, and then actually, Menqi Zhang did something similar in terms of resolvent analysis in plate flow, and again found the most amplified mode has this critical layer structure. All right. Let me just, in the interest of time, just skip these and skip that slide and go on to the last bit. And so what we've done most recently is started to use some pattern analysis techniques, some essentially classical pattern analysis techniques, and applying them to viscoelastic flows. So this is just a movie of one of our recent simulations. Wall normal velocity, streamwise velocity, polymer stretching. Again, you see this strong sheet-like structure in the polymer. Okay, and so what we've done now is to do some analysis of this. So let me talk about POD, which many people here are probably familiar with. So POD goes by many names. So in the fluid dynamics community, John Lumley originated it by asking the question, what velocity field captures the largest fraction of the fluctuating kinetic energy in a turbulent flow? All right. In data science or statistics, there's principal components analysis, which is given a data set, what's the direction along which the variance is largest? All right, and variance is in a turbulent flow, that's fluctuating kinetic energy. So PCA and POD are essentially the same thing. And so you're asking the question, if we have a data set, a bunch of data vectors, we want to find the quantity phi where this is maximized. So the inner product, the square of the inner product is maximized. So the variance, that's the direction where the projection of the data onto this mode is the largest. Okay. In the Newtonian case, that you can write that all in terms of kinetic energy. And then more recently, Tim Colonius's group has been doing spectral versions of this, which is the same thing, except frequency by frequency. So you do the Fourier transform in time of your data set, and then do proper orthogonal decomposition at each frequency. And we found that to be quite useful. Oh, so this R actually is a covariance matrix of the velocity field. Okay, I don't think I wrote that down. Basically, if you take this objective function and just write down the maximization problem, this is the Euler-Lagrange equation that comes out, essentially. Again, and R is a covariance. All right, so this basically directions along which you have strong correlations in the flow, right? Because what you're trying to do is you're maximizing the variance, so that quantity is the covariance. You're finding the direction along which that's the largest. It does, and in fact, what we can do is, which is the next slide, you can build the polymer, the stored elastic energy. You can build that into this analysis, and so I'll come back. Yeah, good.
But these are not your exact coherent structure.
These are not exact coherent structure. That's right. These are not. So that's actually an extremely important point. B here, a POD mode is not a solution to the Navier-Stokes equations. Right? Exact coherent states are solutions to the Navier-Stokes. That's right. These are the directions along which the variance is maximized. So they're picking out key structures, people call them coherent structures. They're coherent structures in a different sense than the exact coherent states I was talking about. For polymer solutions, if you use the Hookean spring model, you can write down the total mechanical energy. There's the kinetic energy piece here, and then there's a piece here that just depends on trace alpha, which is actually the square of the polymer stretching. Okay, and you can then, so we want to make this a quadratic, so you basically take the square root of that term, the metric square root of that term. That's a scaled stretch tensor, and then we use the velocity field and then the scaled square root tensor, and then use this as the inner product that goes into the PCA. And now this naturally builds in the polymer stretching, and it builds in the proper scaling of the ratio between the polymer stretching and the velocity. All right, so this very naturally is the approach to use for polymers. Okay, so it's a little bit involved because you have to take a square root tensor of all your polymer conformation tensors, but it's fine. It works quite well. All right, and so this is, and you could do this in POD. You can use it in the spectral sense. And so we've done this in now in the channel flow, and what naturally falls out right away is that the leading POD mode, I haven't done the spectral part yet, the leading POD mode is very similar to the Tolming-Schlichting. You have this cells of positive and negative normal velocity, and you have these polymer stress, see these sheet-like polymer stress fluctuations localized in a critical layer. And then if you do the spectral version, what's really interesting is the following. This is in a short domain, length 5. The spectral version, it shows these peaks right away. So there are energy peaks as a function of frequency. These are not harmonics in this case, right? And so let's look at what all of these structures look like. So this is the first peak. So this looks very similar to the Tolming-Schlichting wave. Okay. While normal velocity, polymer stretching in these localized sheets in the critical layer. This is the first mode. This is the second mode, which has the same basic structure of the first, except it's squeezed in toward the center. The third mode is squeezed a little more. The fourth mode is squeezed a little more, and then this fifth mode, it's very much squeezed toward the center. They all have similar structure to this first mode, but again, sort of squeezed toward the center, away from the walls. That's just showing that. And then this is robust across parameter values. And so what's really interesting here is that you can find the critical layer position just based on the wave speed comes out of the SPOD analysis, just from the wave number and the frequency. And so that gives you a critical layer position. And we see that the polymer stretching is localized in those critical layer positions. And what's most interesting is that this is the stress fluctuation from the first peak. This is the velocity fluctuation from the second peak. And that velocity fluctuation fits right inside the critical layers from the first peak. And the same thing continues to happen. So let me just show this movie. All right, so let's just describe this. Okay, so this is the velocity fluctuations from the first peak. Now I'm adding the stress fluctuations from the first peak. And let the velocities float away. Now the velocity fluctuation from the second peak. All right, and now the stress of the letting the velocity go away. Those are now in the middle there, that's the velocity fluctuation from the third peak. And what you're seeing is each of these successive peaks, the velocity field is localized inside the critical layer of the previous peak. So you have these nested traveling wave structures. So that's what we're trying to illustrate here. There's the first velocity field, stress from the first. There's the velocity field, stress from the second, velocity field, stress from the third, and so on. And you can turn that into a little theory that basically says that the critical layer scaling should go like this. The wave speed scaling, oh, I had that wrong. Wave speed scaling should go like this. Critical layer position scaling should go like that. And the data falls right on that curve. And so in this channel flow case, we basically have these nested Toulmin-Schlichting-like waves that are forming the elasto-inertial turbulence structure. Okay, and then just very, very briefly, something very similar shows up in the pipe flow case. So now this is again the viscoelastic SPOD, wall normal velocity fluctuations, streamwise stress fluctuations. These are three modes. These are now at the same wave number. Again, we have three critical layers. This critical layer is nested just inside this one. This critical layer is nested just inside this one. So this layer structure that you see in elasto-inertial turbulence is a reflection of these different traveling wave modes with these localized critical layers with the sheets of polymer stress fluctuation in each of those critical layers. With that, I will just wrap up. I've probably talked too long already, and I'm happy to answer any questions.